we'll talk about the complex geometry of Momentangle manifolds, and I will, at the end, I will say some words about mixed Hodge structures on the open toric varieties. Okay, the toric topology is quite interested in studying the usual topology of Momentangle manifolds and Momentangle complexes, but it was discovered recently that we can endow the Momentangle manifolds with the complex structure. So there is a question how to describe the different algebraic geometrical invariance of these complex structures on Momentangle manifolds, and there was several works by different people who studied these questions. So first I will introduce the Momentangle manifolds. We actually have seen it just in previous talk, the definition of more general object of polyhedral complex, and Momentangle manifolds is just in Antony notations, it's just following object. We have a pair, disk and two-dimensional disk and one-dimensional sphere, and Momentangle manifolds, Momentangle complex for simplicial complex K is just this polyhedral complex. So we have some simplicial complex on the set of vertices n. I will use this notation during all my talk, so I will write it here. Okay, and some vertices could be actually not the vertices of this complex. We call these vertices a ghost vertices. Define this set is just a product of disk and of several copies of disk and several copies of spheres. And we can define the topological space, which is called the Momentangle manifolds. Or it is just a polyhedral product of this one. Okay. So if K is triangulation of minus one dimensional sphere, then it just then this topological space is actually m plus n dimensional topological manifold, and this manifold is called the Momentangle manifold. For example, for I don't know, for if K is just 2 points, then this zk is three-dimensional sphere. Okay, and if it is 3 points plus ghost vertex, then it's three-dimensional sphere times one-dimensional sphere. Okay, it's simple. So we also need the associated to the simplicial complex coordinate subspace arrangement. We can define it in this way. There's a union of coordinate subspaces, and union is taken by all sets that this set is not a simplex in simplicial complex. Or and we will need actually not this coordinate subspace arrangement, but the complement in Cn of this subspace arrangement. And again, we can we see this structure before in Tony talk. It's just a polyhedral product of these two guys. We have a C star, and this is just what I write Cn minus zk. Okay, and it's quite easy to see that there is our Momentangle complex is a subset of complement to the arrangement, and there is deformation interaction of complement to arrangement to the Momentangle complex. Okay, so we need to introduce a Stanley-Reisner ring of simplicial complex. We have a we have a polynomial ring, and we take a quotient of this ring by ideal generated by the monomials, such that this monomial is this sigma is not a simplest in K. Okay, so for example, for this case, we have monomials like V2. We have a ideal generated by monomials, by these monomials. Okay, it is okay. This example. Okay, and now we can define the differential bigraded algebra in this way. It is exterior algebra and tensor product to the Stanley-Reisner ring, and take as a quotient on some ideal. This ideal is defined by generated by these elements. It is just exterior algebra. It is RK is bigraded differential algebra. Bigrading is given in this way, and differential is given in this way. So we can define a bigraded cohomology of this algebra. Here it is, and the full degree, full grading cohomology is given in this way. Okay, and this result of Buchstaber-Panov that the cohomology ring of Momentangle complex is isomorphic to the cohomology ring of this algebra. Actually, they prove it for integer coefficients, but for simplicity of notation during my talk, I will use in my talk the complex coefficients. Okay, and okay, now I need to introduce the Hopf manifold and Calabi-Ekman manifolds. It's just for some historical part of my talk, because I will not use it during the talk, but I will use the generalization of this in my talk. Okay, so the Hopf manifold is obtained as a quotient of Cn minus 0 by fraction of group Z, whereas Zx by contraction of Cn minus 0. We may think the principal example of this that Z acts by multiplication of some invertible matrix, such that all eigenvalues of this matrix is the absolute values of eigenvalues of this matrix is less than 1. Okay, so, and it is to see that the Hopf manifold is diffeomorphic to the product of two spheres, actually. And in some cases, the Hopf manifold is just a principal bundle S to n minus 1 S1, and here we have a CP n minus 1, and the fiber is one-dimensional compact torus. It is a compact torus. It is the projective space. Okay, but in some cases this is true, but in some cases we don't have this fiber bundle. Okay, and Calabi-Ekman manifolds is constructed in the similar fashion. We have this space. Okay, this is just product to this is actually a complement to some coordinates of space arrangement, and we take the we have an action of group C and we take quotient space. Here it is. And this space is diffeomorphic to the product of two odd-dimensional spheres. And in this case, we have we can represent it as a principal bundle with fiber again in torus and over Cpn-1 and Cpn-m-1. Okay. As a generalization of these two, okay, it is very famous complex manifolds, and they're interesting because they are actually not algebraic and non-Kähler manifolds. So probably it is one of the best, most famous example of non-Kähler manifolds. Okay. And the generalization of these two examples in some fashion is called LV-MB manifolds, and they was actually introduced by Lopez de Medrano, Vyriovsky, Meersman, Bossio, and also was studied by Panov, Ustinovsky, and others. Okay. So I need to introduce a complex structure here, and we introduce it in the following way. We have let K be a triangulation of our sphere, and let A1, AN be some vectors, and assume also that n minus m is even, okay, and denote it to we assume that we suppose that it is equal to L. Okay, and we have some, and we have a linear map that sends the element of basis to the element to the vector AI, and now we need to choose a linear map psi from CL to Cn, satisfying these two conditions. First, the composition, that real part, is a monomorphism, and the second condition is that the composition of a real part and phi is just a zero. Okay, now we can define a complex group C. C is a subgroup of actually C is a complex group C is a subgroup of C star n in the following fashion. It's just exponent of phi Cl. We can consider that this is as a Lie algebra of this Lie group. Okay. Okay, and now we can introduce a complex structure on the Momentangle manifolds. Suppose we have this data, just that we just introduced, and suppose this data define a complete fan in Rm. It is not necessary. We don't need actually rationality of this fan. It could be a real fan. Okay, and suppose that the difference of n minus m is even. Okay, then we can consider the space Cn minus zk and to take and consider the quotient space. Yes, and there's two facts. First of all, this is the complex manifold because it is good action, and the second, this complex manifold is actually diffeomorphic to our Momentangle manifolds. So in this fashion, we introduce the complex structure on our complex manifold. So now I would like to study some complex invariance of this manifold. Okay, recall that we have this algebra that we use for studying for computing the cohomology of ordinary cohomology of complex of Momentangle complex. Okay, now we denote V as it is just a Cn, and we consider it as a complex space spanned by generators by the basis U1, Un, and thus we can write this algebra in this form. Okay, and we have the map psi from Cl to Cn, and let L be as a subspace in V such that it is orthogonal to the image of phi Cl, okay, to the standard inner product. Okay, it is not a Hermitian inner product, it is without conjugation. Okay, it's a usual inner product. So we have a exterior subalgebra Cl in Cv in the usual way, because it is subspace, L is subspace of V. And we can define a new differential gradient algebra in the following fashion. It's actually like this, but we change lambda V by lambda L. And it is subalgebra of Rk, and we have a big gradients, and differential is induced in the natural way. Okay, and the theorem, which was first proved by Panov and Stinovsky with some additional technical conditions on the nature of phi and generators, and in general case it was proved by me. The Delboca homology of our Momentangle manifold can be computed by the following formula. So we need to compute the cohomology of this algebra, and then it's just a direct sum, and here is just a exterior algebra of some generators xi1, xi. So it can be computed in very similar fashion, like a cohomology like an ordinary cohomology of Momentangle manifold. Okay, and now I would like to say some words about the Schiffs, the cohomology group of the holomorphic vector fields. Assume that there's some additional conditions holds for our map psi, and actually this condition holds. Yes. In this case, we have the following results. First of all, the space of holomorphic vector fields over Zk is just isomorphic to Cn minus L. And the second result, the higher cohomology groups of this sheaf, of the sheaf of holomorphic vector fields, is isomorphic to this one. So there we don't need any cohomological computation. Like here we need to compute some cohomologies actually. But here we have this. Okay, and also I would like to say some words about submanifolds. Recall we have such coordinate subspace. We can consider the intersection of this coordinate subspace with our complex manifolds, with our complex manifold in the. Okay, and we have the following complex submanifolds in our complex Momentangle manifold. We just take the intersection of this space with complement and take the quotient. And if this additional condition holds, yes, then there is no other complex manifolds. Yes, the theorem say, again, it was proved with some technical additional condition on the psi and a's by Panov, Stinovsky, and Verbitsky. In general case, it was proved by me. that assumes that this condition holds, then we have then any complexly reducible analytic subset of our manifold Zk is of positive dimension is just the manifold of this type for some index I. Okay, and now I would like to say in the last 7 minutes a few words about mixed Hodge structures on the smooth open toric varieties. Because okay, the Hodge theory for the complete smooth toric varieties is well known, but okay, let sigma be a non-singular rational fan, and sigma is not necessarily complete, and A1, An just generators of one-dimensional cones of this fan, and we have this map as before. It sends the element of basis to the vector AI, and let M be the subspace of V. C orthogonal to the kernel of complexification of this map. It's like something similar that we used in the previous construction. We can define the differential graded algebra in the similar fashion, and let X be a non-singular toric variety defined by fan sigma. Then its cohomology with complex coefficient can be computed in like just cohomology of this algebra. Okay. Okay. RK sigma is algebra similar to the RK, and we just change here exter lambda V by lambda M, and M is some subspace of V. And integral cohomology of non-singular toric varieties were computed by Matthias Franz, I think he's here, and in slightly different terms, but to the okay. And what I want to say, probably I need to hurry up. Okay, I would like to say some words about the about the mixed Hodge structures. Suppose we have some vector space over Q and finite dimensional. A pure Hodge structure of weight R on HQ is decomposition of the complexification of this space into the direct sum, such that the following conditions holds. That the HPQ is just HQP conjugated. Okay, and this notation is motivated by the classical Hodge theory, because R-dimensional cohomology of compact Kähler manifold X has a natural Hodge structure of weight R, and for example, any smooth projective variety has a Hodge structure, cohomology of any smooth projective variety. And we can introduce the Hodge filtration in the following way, and there are several condition holds for Hodge filtration. It's just a sum of some subspaces. Okay. And mixed Hodge structure is consists of two things. The first is the weight filtration, and the second is the Hodge filtration. I actually will use a weight filtration over H scene over complexification of the space. Okay, and the following must be hold. The following condition to define a mixed Hodge structure, we need the following conditions: that the elements of weight R quotient by elements of weight r minus 1, the space has a pure Hodge structure on weight r. Okay. It is so here, and according to the delinear, the cohomology group of any of arbitrary quasi-projective variety has a canonical mixed Hodge structure on it, and suppose we have a smooth complex quasi-projective variety. The weight filtration has the following form. And the theorem is, and my theorem is that we have the following decompositions for the Hodge filtration and the weight filtration of the cohomology of not necessarily complete smooth toric variety defined by the Fan sigma. Okay, it is just a direct sum of these algebras with some indices here. And in particular, if we consider the complement to some subspace arrangement, which is particular case of smooth open toric variety, then we have this decomposition. This means that we actually can compute this algebraic geometrical data in terms of the original algebra, in terms of begrading of the original algebra RK. And it's in more down to earth terms, it means the following, that any element of this guy, of chi term of Hodge filtration, can be represented by a differential form of some special, can be represented by a differential form of the following type, where phi pq is differential form of B degree pq, and p is a number of holomorphic differentials, and q is a number of anti-holomorphic differentials. So what I want to say in the end of the talk is that many things in complex geometry of Momentangle manifolds and toric variety and open toric varieties and can be defined in the terms of different algebras like RK and similar algebras. So I want to stop here.